afternoon, everyone. Let me introduce myself. I am Lecция Nasedkina. I work in the Department of Mathematical Modeling, Institute of Mathematics, Mechanics and Computer Science, named after Josip Israelovich Varovich, in Southern Federal University. I'm a senior lecturer, and welcome to my course, which is entitled Numerical Methods of Linear Algebra for Sparse Matrices. My presentation will consist of two parts. First, I will give you a brief course overview with all its aims and learning outcomes and prerequisite study materials and so on. And then you will have a chance to follow a sample lecture which will be devoted to sparse matrices, its representations by graphs, storage schemes for sparse matrices, and algorithm for basic matrix operations. So let me first start with the course overview. This course is intended for graduate students. It is a part of the program IT in Biomechanics for those students who study for a Master of Science degree in Applied Mathematics and Informatics. So it was specially prepared for this IT and Biomechanics program in the framework of Tempus Icarus project. This is 5 European credits course. This is it, which means that the student will need about totally 153 hours to complete this course. The status of the course, it is in a major subject, but it is an elective module, so the students can choose. Actually, next semester they can choose 5 courses out of 6. So they will probably choose my course. It is delivered in the second quarter, which means it is the first year of graduate study and the second semester. On the mode of delivery face-to-face, the course has lectures and laboratory work and some home assignments, and also a report on the final project. For the students, the aims of the course will be, and the main aim is to learn solution methods for linear sparse systems. Let me explain that a sparse matrix is a matrix which has a lot of zero components, and these matrices arise from discretization of partial differential equations. So this is really important. They have very large dimensions, and so any problem of mathematical physics, especially with complex geometry, after discretization we will get the system of linear equations with a sparse matrix A. Also, another aim of the course will be to learn, for the students, will be to learn different storage schemes and iterative solution methods. This is the core of this course. Iterative solution methods, projection methods, and especially Krylov subspace methods. This is what the course is actually about, the study of these methods. And it will end with some basic knowledge of preconditioning techniques. So the student will be able to use this preconditioning techniques in order to precondition a given linear system of equations. So in terms of learning outcomes, there is a big list of learning outcomes. So by the end of the course, the students are expected to demonstrate ability to use the technology of sparse matrices to solve the linear system of equations with sparse matrices, and to implement suitable solution methods to solve this linear sparse system. Also to employ preconditioning techniques, and let me show you the continuation. To implement this solution algorithm and computer programs, and in MATLAB or in Maple or maybe in C, and also to use modern software, and also to use specialized packages. For example, SparseKit, this special package designed for sparse matrices. So the course will consist of approximately 16 lectures, and here I gave you an overview of these lectures. You can see it in the slides. So you can see that the course starts with just basic ideas of linear algebra and basic definitions that we will need for this course. Then, like for example, canonical forms of matrices. Then there is a lecture devoted to discretization methods, like finite difference method and finite element method and finite volume method, but it will be just overview of this method. Then there is another lecture devoted to structures of the sparse matrices and storage schemes, sparse formats, some review of direct solution methods, but as I have already said, this course is devoted to iterative methods. So the main iterative methods are covered, such well-known methods as Jacobi, Gauss-Seidel, successive over-relaxation and symmetric successive over-relaxation. Then the projection methods are studied, like starting with the one-dimensional method. And as I have already said, again, the core of the subject is Krylov subspace methods based on Arnold's orthogonalization. These are form and GMRes, generalized minimal residual, and other type of Krylov subspace methods based on Lanczos bi-orthogonalization. And these methods are for non-symmetric matrices. So Lanczos method is for symmetric systems, and Lanczos bi-orthogonalization is for non-symmetric systems. So the last lecture can be devoted to this preconditioned iterative algorithm, preconditioning technique, and choosing the appropriate type of precondition. So prerequisites of the course, just very simple. So basic courses on calculus, linear algebra, numerical methods, partial and ordinary and partial differential equations, and some knowledge of scientific computing, especially math, will be required. So the study materials. There are 5 books which are recommended for this course to study. The course will be based mainly on the first book by Joseph Saad, Iterative Methods for Sparse Linear Systems. As I know, it is not yet translated into Russian, but all other books, they are translated into Russian. So they have also, there are also editions in Russian language. And the workload and assessment for this course. So this course is graded with a grade from 2 to 5, and it is I expect that the students will spread their workload evenly throughout the semester. They will need to do homework assignments and practical assignments. They will constitute 30% of the course of the total grade, let's say. Then individual project will be 40%, and final written exam 30%. Altogether 100. So that's it with the introduction of this course, with the description of the course. And now let me show you an example lecture which is devoted to structures of sparse matrices and storage schemes for sparse matrices. Maybe it is the most one of the most interesting lectures in this course. At least it will have a lot of pictures. So, lecture outline. In this lecture, I will give you a definition of sparse matrix. I will describe types of sparse matrices, give graph representations. We will also learn about permutations and reordering and what it is used for. The most important thing that we will consider the storage schemes for sparse matrices and algorithm for matrix by vector multiplication for matrices which are stored in this sparse formats. So, let me repeat the definition of a sparse matrix. So, a sparse matrix is a matrix which has very few non-zero elements. And the example is here, you can see. So, 64 elements, only 12 of them are non-zero, which constitute only 18% of all the components, all the elements. So this is an example of sparse matrix. And as I have already said, sparse matrices arise from discretization of the partial differential equations. And these sparse matrices, they fall into two types: structured and unstructured, or can be said irregularly structured. So structured matrices are the matrices which non-zero elements form a regular pattern. For example, they are located along several diagonals or in a block diagonals, something like this. Other types of matrices are called irregularly structured. And this is the example. This is finite element grid and the corresponding sparse matrix of this finite element grid. Of course, this is the pattern how these non-zero elements are located, as you can see, yes, in this slide, in this picture. This is an irregular. It will be a regularly structured matrix. And I also want to mention that if we consider a regular rectangular grid and finite difference method, so discretization, then matrices which arise from finite difference method, they almost all of them have regular structures. And instead, the matrices which arise from finite element method, they have irregular structures. So, some words about graph representation of a matrix. So, matrix can be represented by a graph. This is just a simple definition. We can recall the definition of a graph. You all know it. Yes, the graph has vertices. So, this is the set of vertices. So, then n is the number of nodes, and it has also edges. So for sparse matrix, this is called adjacency graph. Here you can see the examples. The pattern of this is unsymmetric matrix and symmetric matrix, and you can see that symmetric matrix can be represented by non-oriented graph, and unsymmetric matrix is represented by an oriented graph. And this also, the explanation here is that if there is an element Aij, yes, then there is an edge from I to j. Okay? And also, if we, in terms of equations and unknowns in this linear system of equations, So the rows of this matrix A represent the equations, and the columns of this matrix A represent the unknowns in this equation. These are some definitions for permutation and reordering. Maybe we will not dive into details because of the lack of time. So I will just say that we can perform a reordering of both unknowns and equations. So we can, we can make, we can multiply our matrix on a by permutation matrices, yes, and obtain a matrix with permuted rows and columns. So let me give you an example. This is a simple permutation by 1, 3, 2, 4. This is an example matrix. So if we perform this permutation on rows and we obtain the resulting system, rows are permuted, you can see that the order of unknowns has been changed. Yes. Then we can perform the same permutation, the same pi permutation on columns of this resultant matrix, and what we will receive, we can see that this matrix contains both its columns and rows permuted. And for example, you can know that the elements, all diagonal elements, all initial diagonal elements of the initial matrix A, they again lie in the main diagonal of the resultant matrix, but in a different order. Yes, for example, here there is the diagonal element which doesn't lie on the main diagonal. Okay, so why do we need this permutation and reordering? And how it is related with the adjacency graph, let me show you again another example. So this is the graph and the corresponding matrix. Both of these matrices are arrow matrices. So here the vertices are numbered. This is 0 in the middle, and then 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this is the corresponding matrix. So this is it will be the permutation 1, 2, up to 9. Yes. If we label these vertices in other order, like in the reverse order, 9, 8, and so on up to 1, we will receive naturally, yes, we will receive another type of matrix, another pattern. We'll have another pattern. Although this symmetric permutation, it does preserve, yes, the graph, so it doesn't change the edges of the graph. And you can see that the graphs are actually almost the same. The graphs are the same. And the patterns of the matrices are completely different. And if we perform Gaussian elimination, so if we implement direct solution method, we can see that this type of matrix will have a lot of fill-ins. That means that there will be non-zero elements in the places which were initially 0. So in Gaussian elimination, we perform LU factorization, so lower and upper triangular matrices, and so actually the matrix of in this first example will preserve, after Gaussian elimination, will preserve this L and U matrices will preserve the structure of initial matrix. And on the contrast, in the second example, so this matrix will result in in a different way. This matrix will give a lot of fill-ins, and another matrix will have no fill-ins during Gaussian elimination. Okay, so this is another example of reordering by Kufield-McKee algorithm. So I will not explain the details of this algorithm. You can refer to the book of Assad. But again, we will have we have here the same finite element grid, but different orders of the nodes. So we receive different patterns of sparse matrices. And again, this matrix, it is very similar. It has actually the same structure as if we return to the previous slide as this matrix. It is directed upward. And another matrix, the second one, has mainly the arrows which directed downward. So again, this matrix will have, as in the previous example, no fill-ins during Gaussian elimination process. Okay, let me now show you some storage schemes for sparse matrices. Maybe some of you are already familiar with these storage formats, but anyway. So the storage formats which I consider in my lecture will be coordinate format, compressed sparse row and compressed sparse column formats. The abbreviation for them are CRS and CRC. Modified sparse row and sparse column formats, and diagonal format and LPAC, ITPAC. Well, we probably will consider these the most important formats. So, this is the example of a sparse matrix. Okay, maybe it's not very sparse. It's rather than sparsity dense, but just for simplification, we consider a matrix which has just 25 elements, so 5 to 5. Yes, 5, the number of rows is 5, and the number of columns is also 5. So, it is clear that if a matrix has very few non-zero elements, we can store only these non-zero elements, and there is no need to store zero elements. So, we can store only these non-zero elements in one-dimensional array AA. And the length of this array will be equal to the number of non-zero elements. Here, this number is equal to 12. So then we can just, we can introduce another two arrays of the same length, where we will store the number of the row and the number of the column. This is pretty clear. But if we, so we will have three arrays of the length nz, where nz is the number of non-zero elements in our sparse matrix. Nz. So we will need to store actually 3 multiplied by nz elements altogether. Can we store less? Of course, yes, we can store less, and here is sparse row, compressed sparse row format, where you can see that we can really store less elements. So in this compressed sparse row format, the idea is that we can store the elements of the matrix by rows. So here in AA array, we write these elements by rows. So the first row, then the second row, the third row which has 4 elements, the fourth row which has 2 elements, and the last row, the fifth row, has 12 elements. One element only. In JA array, we store the numbers of columns. And what do we have in IA array?
First number.
What first number?
First number in each row.
Not really. So in IA, so these are column indices, are called, yes, column indices. And in IA, we store the pointers of the beginning of each row, in these two arrays. So let me show that I will be the pointer of the beginning of the I row. Okay? So the length of this array will be n, which is the number of rows in the matrix, plus 1. And plus 1. So the last element in this array equals to the first element plus nz, where nz is the number of non-zero elements here. And this IA, I plus 1 minus IA, I will be the number of the elements in the ith row.
Sorry, but what about if there are much less elements in the matrix? Maybe the first format will be more preferable.
Yes. So it depends, of course, on the matrix. Okay. So sometimes it also depends on the solution method. So sometimes really the preferable format is the previous one, so the coordinate format, but actually this one is the most commonly used. Because you can see that first of all it has less elements to store, and you can notice it, yes? Less elements. So it has nz plus nz plus n plus 1 instead of 3nz in coordinate format. Yes? So less elements to store. Okay, in this example, as I have already said, the dimension of the matrix is not very big. But if we think about matrix I by 100 by 100, it will make sense. Okay? So again, the interesting case here is when, for example, we can have a row with all zeros. We can have a row with all zeros. And in this case, in this array, we will have two equal elements. It will mean the length of the ith row is equal to 0. So if we have no elements in the ith row. Okay, so the magnification, the variation will be column sparse, compressed sparse column format. And the idea here is clear. We can store the elements by rows. Yes, by rows, and we will have the same arrays, but we will list these elements of the matrix by rows. Okay. So let me show you also the modified sparse row. So the idea of the modified sparse row, again, it depends on the solution method. If we need to have an access to diagonal elements, and this is our priority, then we can use only two arrays. First, we will list all diagonal elements in their natural order. This is it. Then, there will be n elements altogether. N is the number of the row. The n plus 1 element is not used here, and then we list all the elements that lie either above or below the main diagonal by rows. Yes, this is modified sparse row. And here we will have first. Here this will be the combination of column indices and So the combination. First we will have here the pointers and then the column indices. The modification will be modified sparse column. If we store in this part of array, we'll store the elements by columns. Okay, the another format is diagonal format. It is used for matrices which has diagonal structure. For example, this matrix has 3 diagonals, the main diagonal, 1 diagonal below the main diagonal, and 1 above the main diagonal. In this case, we can store these diagonals in direct two-dimensional array, so in any order actually, and another array which is one-dimensional, it will store the offset of each diagonal with respect to the main diagonal. So the main diagonal has an offset which is equal to 0. Okay, LPAC, KITPAC probably will not cover. So let's concentrate on the algorithm. Only one example CSR format. This is the code in MATLAB programming language. So the idea, again, here we have this portion of the script. So we look at the if row, which is stored. So again, we operate with sparse format instead of dense format, instead of ordinary format. Why this algorithm is so important? Because matrix by vector product is an operation which is commonly used in almost all iterative solution methods, and this is very expensive operation. If we perform it in dense, if we store our matrix in dense format, so this multiplication is a very expensive operation. So this is why if our sparse matrix is in a sparse format, then we need to operate it to perform this matrix by vector multiplication also in a sparse format. So the vector is just a one-dimensional array. So this is the syntax. And we can write the same code for CSC format, but then there is a little error in this code. Maybe you can notice it, maybe not. Okay, here it's JA for the J column. Okay, so here the idea is that the resultant vector Z is being computed by several. I'm sorry. So by several components. So several times. Okay. Okay. Let's wrap up our lectures. And I'm sorry. I'll give you a brief summary of this lecture. So from this lecture, we have learned that sparse matrices can have regular and irregular structures, that they can be represented by adjacency graph, that we can perform permutations and reordering, and this is used to reduce fill-ins for numerical algorithm for Gaussian elimination, and sparse matrices are usually stored in special sparse formats, and the commonly used are CSR and CSC, so storage by rows and storage by columns, and very important operation is matrix by vector product, and we have covered a bit the algorithm, how to perform this operation. That's all for today. Thank you for your attention. Do you have any questions? Yes,
One.
please.
Is the distribution of the non-zero entries predictable to some extent?
The distribution of the elements, I mean the pattern.
Yes, the pattern of the matrix, is it, I
Yeah.
mean the distribution in the sense of how they are distributed
Yes.
over the matrix. If we take a look at on the original boundary value problem, can we predict this distribution at least to some extent?
Well, in fact, it depends on the ordering of the nodes. Because even if we take, for example, finite difference method, and we...
For finding different method, it is
Yes.
clear.
Yeah, this
Always
is clear.
clear.
So it all depends on the how you label this internal nodes, yes? So if you label them in a different order, then you will have a different pattern. And this is actually, I also wanted to mention that this is what students are doing in their practice. So they have to, they are given a certain partial differential equations. They have to perform a discretization of this partial differential equations and to use a certain algorithm for reordering of the nodes. So they can obtain matrix of a different pattern. So it will be the same. Of course, the values of the elements will be the same, but they will be distributed in a different pattern, in a different order in the matrix.
Yes, but this is.
How is it?
Of course, you can redistribute everything deliberately. But is there some original distribution which is produced only not by our own willingness, but by original boundary value problem and by
We can
the specific method
we
you
can
have applied
predict,
to the
for example, the properties of the matrix, like will it be symmetric or not non-symmetric, will it be positive, negative?
Sounds
So-
like this, but in more detail. Could you estimate the distributions of non-zero interest in some way? What, let me propose an example. You are given with a Laplace equation and with some domain with first order with the first order with the boundary condition of the first term. Yes. And you approximate it with the use of some typical
Like algorithm.
typical finite elements.
Yes. But anyway, we have nodes in finite, and we need to number these
Can
nodes somehow. So it
we
depends on the number.
predict somewhat about the distribution of non-zero elements in the resultant matrices? Looking at the domain or at the just manipulating and thinking on this information.
Okay. I think it will depend on the algorithm of reordering the nodes. And we can apply a different algorithm and obtain a matrix with a better pattern, let's say.
Yes.
Ordering is the independent step of the algorithm,
Yes.
because you could apply some scheme of discretization after the ordering of nodes.
Are there any
But-
researches concerning optimal ordering?
Of course,
You know,
curve.
So
I have got the point. The nodes appears when just as a result of the geometry.
Yes.
Yes.
And the ordering.
Their distribution in the matrix you are talking about are not independent of the. This is just a representation
Because they
of a
have
plane domain.
Yes.
Yes, of a
Yeah.
planar
And the-
domain and it has nothing to do to the differential equation.
There are some quite simple recommendation of common sense. For example, if you have a long longitudinal domain, and if you will
There will be
number the nodes for the shorter side, you received a matrix with entries more close to the diagonal. But if you will ordering for the long side, because the main, how to say, the
I was asking about somewhat like this.
yes,
You are talking about.
yes,
Can we look at the domain and predict somewhat about
I'm
the
awfully sorry.
distribution?
Are you
not the
talking to each
optimal, but
other
quite
or
good
to
numeration.
Yeah,
Yes.
now discussion.
Yes, it is already a discussion. We forgot
And
about
then
Anna.
you can optimize, make it optimal using the permutations.
Yes, because Anna said about the one of the famous
Yes,
algorithm,
yes.
well known.
I think
Right.
this discussion was planned by Anna.
Oh, really? No, I don't think so. Okay, any other questions to Anna?
Thank you very much.
Okay.
Very bright situation, but Anna, from your presentation, I understand that we made one mistake and disappointed with a new, how to say, ball and rating system and pointed.
Point rates.
Our percentage in my
Percentage.
percentage in my course unit, in your course unit, for lecture, we should spend a 14%
50%?
of
No, but in fact,
For example.
okay, this course is now running in Russian.
before
In
and
Russian, and I have, in fact, I have an assignment for it after each lecture. So after each lecture, they have either to do home assignment or to do practical assignment and to implement the algorithm that we were talking about in the lecture in computer program. And look
yeah,
at this.
but if
So,
you
I
have
mean, it's actually it's a practical course. Yes, it's not very
Yes.
theoretical.
yes,
Because I'm not concentrating on
But-
theorems, just some of them, which I give a proof only to some of the theorems because of the lack of time.
but students have written exam.
Yes.
So 40 points you should
I mean,
give.
like this
they-
in the second, and then how to say. But it
But-
was in this brochure.
Yes, but
Because,
it
I
seems
mean,
to
I
me
couldn't,
Oscar,
I
can you transform
couldn't.
this into the
No, it's-
meeting of the chair?
not the chair, but the department or faculty, because
In fact,
if we will
this individual project is really important because my students, those who attend lectures, they don't do final written exam. They only have to let's say present their individual project and explain everything there. And those who don't attend lectures, yes, they have to write
To take written exam.
take this written exam, yes, and to write answers to the questions.
we need
It's
the
fair, I
expertise of some person who elaborates this scheme of assessment.
Can we get back to our English class? I'm sorry. Okay, so first of all, now your comments. You're actually, Anna Andreevna was the last one, right? So, and we can compare all the presentations we have heard. I'm pleased that almost none of them were alike, and it is good.